on.
Recording has started.
Okay. Are we here? Hello? See me? The audio quality should be better now because I have a microphone on. Do you hear? Is the audio quality better? Joshua? Or anybody who wants to answer my question?
It sounds better, Charlie, but until we hear the recording, we're not really sure. It does sound better. We do get your audio and video a little better. I mean, your audio better.
Okay. Well, we'll go with that, hopefully. Good. So actually we made a few progress. We made some progress on a few items. One is that I got this microphone, so the audio might be a little better. One is that the video for the on-campus students, you should be able to get it now because we kind of figured that out. There have been some technical difficulties, I'm told, with the so-called Boilercast system that distributes the video. So you might hit some link problems, but I don't think it should be too bad. So let me actually go to the PC and show you how I can do this. We'll hope that this is correct. So we'll try Internet Explorer here and see if it works. Computer will slow. Yeah. Okay, 641. Okay, see, I noticed I added a link here, video lectures. Yes. So you can't video lectures, and then it brings up, okay, so here it works. If you have a Mac, it doesn't work under Safari. That was one thing that threw me off. So there's these various things. This whole Boilercast thing is, okay, so Boilercast is sort of multiple things. It uses this thing called the Echo 360 system. Okay, so I don't think we much care about any of that. You're welcome to try these different things out. There's an Echo link and an audio link and a broadcast URL. All I really care about is the MP4. That's just the videos, you know. I don't think we need anything beyond that because all the other material is already on the web page, right? So you just click this and it should download. I'm actually trying it here. Okay, on my Mac, it downloads it as a MP4. You can put it on your computer and play it back. So that makes it convenient. You don't even have to have a high-speed link when you're viewing it. Or you can, I don't know, you guys are more sophisticated than I am. Oh, there you go. Oh, now, this is pretty scary. We're seeing versions of me being versions of me being versions of me being versions of me.
Okay, so today,
Okay. Close all tabs. Okay, so, I shouldn't have done that. That was a mistake.
your history here.
Okay, anyway, so let me go to the DocCam, so I can begin DocCam. Oh, I have to turn the DocCam on. Actually, what I can do is, is the DocCam going to work here? Hello, DocCam. Is it working? Hello? Let me try to switch it back and forth. So, okay, so today we're doing, this is Friday, so we're doing section 2.2. And, the homework is due today, and one thing I haven't yet taken care of is I haven't yet provided a mechanism for you handling your homework. I'll give it to the students and hand it in. paper. Although I'm suggesting to you, I think, that you hand it in a photocopy rather than an original. If you, I see there's some originals there. If you want to hold on to your original, and by the way, use the stapler if you can. They don't fall apart that way. Okay, but if you want to turn it in, if you want to take it back and photocopy it, that's okay, and bring it in on Monday. Yeah.
I just registered this course yesterday, so I haven't got my homework done.
That's okay.
I have next Monday.
Yeah. And also, as I've been saying, the function of the homework is for you to learn the material, because they'll be the basis of the test. So, there's a pretty good chance that I won't even grade it. I may actually sort of check off and you handed it in. Okay, I'm not absolutely guaranteeing these things, okay? We could change our mind, although I give you adequate warning if I were going to do some major change. But, just a minute. But, so, it's really, but I'm having you hand it in so that way, there's sort of a matter of pride, right? That you don't want to hand in a blank sheet of paper and look really like you're blowing the course off, right? So I know, and I need to generate this sort of initial level of what I call sort of terror among students that you're all really realize you have to read the notes. Okay, and like for the first week or two, I found that it's very important that I start every lecture the same way, which you're going to find very boring, what I'm going to do just now. Hold on. So let me take this off, and then it should switch back to the video. Switch back and forth now. Oh, come on. Yeah. What do you need to do before every lecture? Read the notes, okay? Read the notes carefully. And then, in this particular lecture, I actually do the homework. Maybe we should reserve a little bit of time to go quickly over the homework. So there were actually 4 problems to do? 5 problems to do. Let me just look at those really quickly, because I'm sure there are going to be some questions. The problems were, in some sense, easy, in some sense, hard. You'd say, well, what does that mean? Well, I'll tell you. So the first one is, let y be a random variable which is uniformly distributed on interval 0, 1, and has a PDF. Otherwise, calculate the cumulative distribution function of y, and use this to calculate both the CDF and TDF of z equals y squared. Okay, that's a pretty simple problem, I think. Okay. Now, in this problem, we present a method of generating a random variable y with any valid CDF, okay, specified by f, y, t. So someone gives you a distribution, and from the distribution you want to generate a random variable. This is a classic problem in probability, okay? To do this, let x be a uniformly distributed random variable on the interval 0, 1, and let y equal f of x, where we define the function. Okay, so this function here is a little bit of a mouthful, okay? It's the enthemum over tmm of r. So basically, what this is the inverse, okay? Now, why did I just say, well, the inverse? Well, because it's a little bit more complicated than the inverse. So remember, f of the cumulative distribution function, fy of t, is a monotone increasing function, but it could have discontinuities. So if it was strictly monotone increasing, then the inverse would be simple. But if it's not strictly monotone increasing, then there's it's a little unclear what to do in some cases, right? Because there could be more than one value that maps to the same value. So you can have this. You can have this. So if you have a cumulative distribution function, it looks like this. And then jumps, and then maybe flat for a while, and maybe jumps again, and then gets to 1, all right? So what happens is that it's not entirely clear how you define the inverse here. So I'm telling you, you can do it as, you define it this way. And this is always well-defined, right? Just a moment, hold your thought for just a minute. So, and then I say, prove that in the general case, y has the desired CDF. So, this problem is a way of computing a random variable with any distribution, okay? Because any cumulative distribution function that's a valid cumulative distribution function can be used to generate a random variable with that distribution function. Now, I'll tell you right away, this problem's actually a little bit hard, okay? So, you know what, like, if you can't solve this problem, because it's like a little bit hard, okay, it may be, what happens is ignorance is bliss, right? And for a lot of people, they may not even realize that this is a hard problem. So they just did the easy problem instead. Okay, that's okay. I'd rather you do something than nothing, okay? But for people who really understand that this is actually a hard problem, I want you to do a hard problem. So that's an example of this being, this is sort of like, you know, a book by Dickens or something.
You can read it at different levels, you know, just to, you know, whatever.
Yeah?
So when you say the two sets are equal, at first it's confusing for me because I think one set is actually in the range and one set is in the domain.
Oh, okay. So now you're asking a more sophisticated question. Yeah, I don't know if that was your question.
I just wanted to know what INF, like what the
Oh,
equal
what the theme is? Okay.
How do you spell it? I'll just look it up.
Okay, so, you know, this is, I'm mixing metaphors a little bit here because infimum is like standard notation if you take a course in real analysis. It means, one of the fundamental principles of mathematics is that if you have any set in the real line, right, so if A is a subset of the real line, then the infimum of A must exist. That's actually an axiom of mathematics, okay? So, what it really is, it's equivalent to saying that the real line is complete. So, what it means is that the infimum is also known as the greatest lower bound. So, among all numbers which are lower bound to the members of the set, it's the greatest. And the reason is, so what do you say, well, what's the distinction between the minimum and the infimum? So for all intents and purposes, you just think of the infimum as being the minimum, okay?
Can you just spell it quickly?
Oh, infimum? It's like Latin. I may be misspelling it. Infimum.
Okay.
You can look it up in, if you Google it, I'm sure there's a wiki page on the infimum. It's the int and the sup. The sup is the supremum. So they're sort of rules. And the infimum, okay, so the reason that some sets don't have a minimum, right? So if you take the set of the interval, the open interval from 0 to 1, it doesn't have a minimum because the minimum of that set is 0, but 0 is not in the set. Okay? So the minimum that doesn't exist. But the infimum of 0 to 1, that's equal to 0. Okay? So the infimum is a generalization of the concept of the minimum that always exists for any set, other than the null set, any non-empty set of the real line. Okay, any non-empty subset of the real line. So, okay, now I want to answer the other question. So, let me see here. Okay, so you're looking at the set of U such that f of U is a member is less than or equal to t. Okay, so that's a subset of the real line, right? Because U is a value in the real line, and here you're saying the interval from 0 minus infinity to f sub y of t. That's also an interval of the real line, right? So this equality is sensible because these are two sets which are subsets of the real line. You know, beyond that, we'll have to take it offline, okay? Okay. And they may not have been a satisfying answer, but it was a technically correct one, okay? Okay, so my point is this, if you want to actually do this problem, it's a fairly technical proof. If you're not comfortable with that and have never had a coordinate analysis, that's fine. I mean, you don't need that. Just do the simpler problem and assume that the PDF exists, okay? So this works in the general case, but you could do it with just the number probability density function. So P of X equals F of X dx. So as soon as the PDF exists, if the PDF exists, then none of these bad things can happen, and it's a simpler case. It's very similar to case 1. And that illustrates the essential idea, okay? I just want you to know two things. One is that, you know, for normal random variables, you can always generate a random variable with any distribution by just applying the inverse cumulative distribution function. The intuition there is this. Let me just explain this really quickly. The intuition is this. So if you have a cumulative distribution function, it kind of looks like this. Okay. So let's say it goes from 0 to 1. It doesn't have to, but let's say it does. Okay. Then you take, this is a lousy distribution. Let me fix my math a little slower. This is 0 to 1, and this is 1 here, and this is 0. So let's say you have something like this. Okay? And then the inverse of it would be like this. Right? That's the inverse function. So what you do is you put a random variable which is uniformly distributed as the input, and then the output, so this will be x, and this is y, and the distribution of y will be the same as the distribution of this cumulative distribution function. So if you give me a cumulative distribution function, I can generate a random variable. This is very practical, because let's say I give you some cumulative distribution function, and I ask you to do a simulation, a Monte Carlo simulation. Everybody knows what a Monte Carlo simulation is. Does everybody know what gambling is? We'll start off with something simple, right? You know what gambling is, like you go to Atlantic City or Las Vegas. I grew up pretty close to Atlantic City, so I'll say Atlantic City. And then, you know, and it used to be they had gambling in Monte Carlo, okay? So you do a sequence of random gambling events, okay, random events. So you do that on a computer. You do a simulation with random number generators, and you run that simulation, and you see how often one thing happens or another. That's called a Monte Carlo simulation, right? And if you want to do a Monte Carlo simulation, and you have to generate random variables with a particular distribution, how are you going to do that? Well, the answer is you apply a uniform random variable to the inverse cumulative distribution function, and it will generate any random variable you want that way, okay? So the good news is, so a couple things to remember. One thing is that's how you do it, and the other thing is that it always works, okay? Now, it may be too complicated for you to prove it always works, but just believe it does, because that's homework too. And I wanted to ask you a problem where the answer was that it's impossible. Well, that's not entirely true. Sometimes I do that just to be evil, but in this particular case, I'm not, okay? Now, and the other thing to remember, the other thing, I'll just give you a little preview, is it turns out some random variables are really hard to generate because this inverse cumulative distribution function is really hard to generate, and especially that would be the case if this was a billion-dimensional space, okay? Because then you have a billion-dimensional cumulative distribution function, that would really be hard to invert, okay? So we'll actually talk about that later in the semester. It's called simulation, stochastic simulation, okay? Okay, but, what am I telling you here? I'm telling you that if you can't do the problem I asked, try to at least do something simpler, okay? All right. 3, I did this in class, so I told you the answer to that, so that's easy, okay? 4, now, doing this problem exactly correctly also is really complicated, okay, for a variety of technical reasons, okay? One of which is that m may be less than n, so the matrix A is not square, okay? So, if you can't do the problem where m is less than n, just do the problem where m equals n, okay? Okay? So, do the case where n equals n, then A is square, and A is full rank, so it's invertible. And the solution to that problem, I'll tell you right now, is this. What you do is, if the A is square, okay, it's invertible, then what happens is that, if you know the distribution of something like x, right? And you want to calculate the density function of y, right? And y is equal to a times x, right? Well, it turns out, and this is a really basic result that you should remember from your probability class, that what you do is you calculate, okay, what I do is I take p of x, and I plug into x a inverse of y. So we have x equals a inverse of y. So in other words, I just plug in the value of x that corresponds to the value of y I'm looking at. Now, that wouldn't technically be correct, because what'll end up happening is that this thing doesn't integrate to 1 anymore. So what you have to do is you take the so-called Jacobian of this thing, and now, so you take the derivative, basically, so you call this thing f of x. So you take here, you have to multiply by df dx. So you take, that's in general matrix, right? And you take the determinant of that matrix, and now you either multiply or divide by that number, and I can't honestly remember which it is you do.
It's actually dx over df.
But that depends on whether you multiply or divide.
It just depends on whether you multiply or divide. Okay, so let's see. So let's think. If this thing expands, I'm going to end up getting this wrong with virtual certainty. Okay, there's either a -1 or a +1 here. And you know how you find out the answer to that? Magic answer to my question.
Multicolor simulation?
Yeah, that's a good idea, but no. I had a simpler, I'm a very practical person, okay? So, okay, now, forget that you're in a classroom and you don't want to hurt my feelings, okay? What would you do if you didn't know the answer to whether that's a plus or -1 up there? Be resourceful. Come on, some of you have got to know the answer to this question. Huh? Well, that's a good idea. You look at a book. What else would you do?
Take a small example.
You could do that. That's actually a very good idea. This is actually a wonderful experience going through this. Okay, what else? Come on, guys. The funny thing is, if I actually assigned this, and I walked out of the room, you do it instantly, okay? You're just not saying it to me because you think I don't want to hear it.
Ask somebody.
Okay, that's a good answer. You'd ask somebody, because they'd say, I can't remember. So then what would you do? Wikipedia, okay? Just Google it, okay? It's going to come up. There's going to be a whole wiki page on this, okay? We all know. I mean, who are you keeping a secret from, right? I know. There's nothing wrong with it. Go find it. And then, but you can also figure out the example of 1D. Okay, in 1D, you'll figure out whether you have to multiply or divide, right? Because what's going to happen is that when you multiply, you'll see that, just plug in a 1D example, that if A is like 10, the probability distribution will be off by a factor of 10, one way or the other. It'll be either 10 times too large or 2 times too small. So figure that out, okay? So, so what I was going to, so when you do that, you just plug this in and you'll see that what'll happen is that the covariance matrix of the Gaussian of y, so the covariance matrix of y will be like the covariance matrix of x times A transpose A, something like this, okay?
You just do it with characteristic functions, right?
You can do it with characteristic functions too.
And then
No,
there's nothing
I
wrong.
avoid, maybe I'm wrong about this honestly, but I avoid using characteristic functions in this class for the following reason. I like to do everything from basic principles. So, I mean, it may not be completely obvious to you, but if I'm developing the material in this class, you could fill in a few little details and you'd have absolutely rigorous proof for everything. Okay? Like, if you just took a course of real analysis and plugged a few extra little theorems in, but if you use characteristic functions, you're using a gigantic power tool, okay? I mean, which is true, but requires a lot of theory to prove, okay? Because it requires basically the theory of Fourier transforms, which is functional analysis. So I'm kind of avoiding that as a matter of principle, because you don't need all that machinery to do this. So I'm trying to do it in what I consider to be a simpler way, but you probably consider to be more complicated. Because it looks more complicated, but it's simpler in concept, because it's not using all these assumed results, these theorems that are very powerful and complex. Okay?
Can we extend that to any continuous distribution instead of Gaussian?
Oh yeah, well the same method will be true, but the difference is that this Jacobian here becomes a function of x. In this case, the Jacobian becomes a constant. So it's essentially, so this constant becomes irrelevant, because you'll have to figure out what the multiplying constant is anyway. We'll see. This is, the trick you do when you solve this problem is the same trick we use over and over and over again in this class. So, again here, if you can't do, there's a more complicated problem where a is not square. If you can do that, yeah, you have to like, you have to do a lot of little complicated technical tricks, okay? But if you don't want to do that, just do the simpler problem. I write it this way so you know this is true, okay? It's true in the more general case, but this is a simpler case, okay? And what else? Do we have any other problems?
Can I do like a linear combination to prove the question true? Because if it's Johnny Gaussian, then any linear combination.
Well, now you have to go back and look at my definition. So in this class, I'm like very forgiving of like little mistakes, but I'm less forgiving of big logical errors. So I really want to do, I'm more concerned about the logical structure of proofs than the technical correctness, okay? Okay, so you have to go back and see what my definition is. And different people use different definitions. So in this, for various reasons, which I don't want to go into, and we haven't even gotten to yet, because that's the primary discussion of today's lecture, is that my definition is that a Gaussian random vector is a random vector whose density function has this form. Okay? So that's the assumption. I mean, that's the thing that's the thing you have to premise. And from this you have to prove the other one has the same distribution. Okay? Sometimes they take the definition of Gaussian random vectors to be a vector which has the property that any linear combination of it is. I don't know. There's other definitions. Okay. There's other ways of constructing the Gaussian. No, but I'm sure I'm consistent because I've spent way too long. Okay, so where's your point?
Yeah, the middle.
No, I say a Gaussian random vector with a distribution of 22% is also known as a jointly Gaussian random vector. Okay, so that's the definition, right?
Yeah.
And then 5 it says, well, what do you?
So there's the middle one. Why would that come from two? Like if
Two from CV and then.
Say it again. Where?
it's there, like for example, it's possible to have two Gaussian random variables.
So
The sum, the sum is also like.
Furthermore, it can be something.
Oh, yeah, these are Gaussian random vectors, variables, but they're not jointly Gaussian.
As a PP.
Huh?
Yeah, the PP sentence.
Okay. Furthermore, it can be shown that a random vector is jointly Gaussian if and only if any linear transform of the vector produces Gaussian random variable. That's a true statement. But it has to be proved.
Yes.
Okay? The definition here, okay? So I'm asking you the question, you cannot use something that's unproved, okay? I've stated it, but if you want to use that, you have to prove it first. Okay?
Actually, I also kind of looked into my 600 notes and I found that. Like,
Right.
Yeah. So
Yeah.
it's a linear combination of
Right.
right.
See, but I want to be able to see, I mean, you'll eventually get the idea here. I'm a little demented, okay? Which is that I really want, when I've asked the question, I don't want, okay, so one thing that's really important about logic, okay, is this, okay, that when you have, I don't want to spend too much time on this because we've got other stuff to cover, but when you have this, okay, it's logic has to, these are your assumptions. Logic has to be an acyclic directed tree, okay? Okay? So, I can do this, okay? What I can't do this is do this, okay? That's invalid, okay? I can't use a result to prove something more basic, okay? So I told you the assumption is this definition, okay? Now, I also mentioned that that something here can be shown, but you can't use that thing until you've proved it, okay? You can't have circular arguments. Students often like to do that, where they say, well, prove that all Purdue students are nice people, okay? And you say, well, prove that all Purdue engineering, I don't know, I'm really getting stuck here, okay? So you say, well, all Purdue students are people, and all people are nice, or I don't know, you go around in circles, and, but you have to, when you're proving something, you have to keep track of the flow of logic, and you cannot back up, okay? You cannot use circular reasoning, right? Okay, why do you want to do that? Because it'd be fun. Well, yeah, but that's not a good reason, but I want to do it. Kids do this, right? They go, you keep asking them questions, and they kind of go around in a circle, okay? We don't know how to do that, okay? So, I'll come up with a better example later, but I think you know what I mean, okay? Okay, good. Are there any more questions about that? Because, what other, was problems 1 through 4? 5? Oh, and, so if R is a P by, okay, so X is a jointly Gaussian zero mean, usually you can configure the case where things are zero mean. So R is a jointly Gaussian, X is a jointly Gaussian random vector, and R is a P by P, so it has to be a P by P symmetric positive definite matrix, okay? That I told you by definition that had to be true. And then it says prove that, if the correlation is 0 for every pair of components, then the things have to be pairwise independent. Well, that's simple, because you just show that if two Gaussian random variables are two jointly, if I say Gaussian random variables, I generally mean jointly Gaussian, okay, unless I'm specifically excluding that, right? But if you show that you have two jointly Gaussian random variables and their correlation is 0 and their mean 0, okay, then it's pretty easy to show that they have to be independent. But you have to prove that. You have to use the definition of independence and the definition of all these things to show that it's true. And then you say, prove that for all Rj, they're all correlated, and the components of X are jointly independent, okay? Well, you have to go back and look at the definition of that and show it's true. Okay? Yeah.
Well, for the first part, is it essential that it has to be zero mean? I think it's true even if it's not zero mean.
Yeah, perhaps, but I'm assuming it's zero mean, so I won't consider that case.
Okay.
You're asking me, yeah. I'm like an attorney. I only answer the question I'm asked. Well, you asked me another question, but I'm very refused to answer it. Because, yeah. Because I also don't want to possibly say something that's wrong up here, but I think you're right. But you only have to answer this question.
Okay.
Okay. Okay? All right. So you got the idea? So not everybody may understand every detail of these questions, but at least answer the part of the question you know how to answer. Okay? I have for some of these problems, I actually have some solutions. So, I may be able to share some of those with you. I'm not sure. It depends on a lot of things. Okay, now, today we've already started talking about Gaussian random vectors. So you guys read this section carefully, right? And if you didn't have a lot of background on probability, you might want to read it multiple times. And you've got to think really carefully here, because my sentences here, now there might be some errors, and please point them out if you find them, okay? But I've been pretty careful, and a lot of people have gone through at least these sections pretty carefully. And in general, my intent is to say things that are true, okay? So the wording in some of these sentences is subtle and precise, okay? Okay, so I don't sort of just mean anything. I mean precisely what I'm saying, okay? So if you don't understand the sentences, read them multiple times And if you can't figure out what they say, come and ask me a question, or email me is a really good way, okay, and I can try to clarify.
In some cases, you may find a logical error, okay?
But mostly they're true. This is the probability density, I've defined a probability density function for a multivariate random vector, and this is, I'm saying anything with this probability density function is a Gaussian random variable vector, and we're going to use Gaussian random vectors a lot in this class. And I think if you just come out of this class learning more about Gaussian random vectors, that actually would be valuable for you, because they come up a lot in applications. And even, I don't know if there are biology or biomedical engineering people in here, or people in other fields, but actually understanding this is really useful. I mean, I think you will use it, because this stuff comes up a lot, and it's typically oversimplified when it's used. So if you understand the underpinnings of it, it's a lot easier for you to use it correctly and really get the right answers when you're doing things, okay? So, R here is the inverse covariance. So, it's easy enough to show, and mu is the mean. So, the corresponding random vector x, its expected value is mu, right? And then, I'm not even going to try to write this out, but the correlation, or the covariance, I guess, as it's called, the autocorrelation, I forget what terminology I use here, but whatever terminology I use, I'm very precise and use it consistently, okay? Because every time I add something, I check. This thing here is R, right? Now, everybody understands the difference between this little x here and the big X? Those are not the same thing, okay? And I didn't have to use a little x there. I could have used any letter I wanted. So what I could do, if I really want to be perverse, okay, is when I could use a variable which would be like a happy face, okay? I could use the happy face variable, because I can use any variable I want. This isn't just a variable, it's just a letter, okay? I use this x, and it's conventionally used because this is a lowercase version of the random variable x, okay? So it kind of helps you think that these things are related. But sometimes that causes more confusion than help, because these are two different things. That's a random variable, and this is just a plain old number, okay? So, okay? So this is just an independent variable of a function, p of x, and that's a random variable, okay? Now, one thing that's very important is that if you have a covariance matrix, so let's assume that mu is 0, the mean, that the mean is 0. That's you usually can assume that the mean of these random vectors is 0. It makes everything simpler without loss of generality, okay? So let's say that the mu is 0, and you can always decompose, this is a symmetric positive definite matrix. So, first of all, it's a symmetric matrix. Since it's a symmetric matrix, we know we can always write it in the following form. E lambda E transpose. For any symmetric matrix, you can do that, where lambda here is diagonal, okay, and E transpose equals E transpose E equals the identity. So this is orthonormal. Orthonormal means it represents an orthonormal rotation in the space. So it's like, you know, a rigid body rotation, okay? It also includes potentially reflections, but let's not worry about that. So that practically means the rows and the columns of this, so all the rows of this matrix are orthogonal, all the columns of the matrix are orthogonal, and all the rows and columns are normal. So that means if I took, so if E is a matrix here and it has E1 through En, okay, then we have that EI enterprise J is equal to delta Ij. That means it's 0 except for when I and J are equal, and then it's equal to 1. Okay? Are people familiar with orthonormal matrices? This is basic linear algebra. Okay? So then what happens is that you can take X and you can transform it by E transpose. And when you do that, it's easily shown that the transformed vector is, the components of the transformed vector will be uncorrelated. And since it's Gaussian, the Gaussian will be independent. So their covariance matrix is diagonal, and the variance of the individual components is the diagonal entries of this matrix. So the diagonal entries of this matrix represent the variance of the decorrelated components, right? And furthermore, if you have if this is Gaussian, then the conditional expectation is always a linear function. So if X and Y are Gaussian, then the conditional expectation is always a linear function of Y. That's really the point. That means if you want to do linear prediction, optimal minimum mean square error linear prediction, and your quantities are joined to the Gaussian, you only have to worry about using linear operators. The other way of putting it is when you only restrict yourself to linear operators, you're essentially assuming that the quantities you're using are Gaussian random vectors, which actually we're going to find out Gaussian random vectors are wonderful, but they're also have severe deficiencies. That real data tends often not to be Gaussian. Images in particular are not Gaussian at all. In fact, most of this course is going to be all about figuring out how to drop the Gaussian assumption. Okay, but before we can drop the Gaussian assumption, we have to embrace it. You know, I like to use the analogy, it's like, you know, if you go look at a picture, a painting by Jackson Pollock, or even, I don't want to offend anybody, Picasso or something, you know, it's like this big, discombobulated thing, okay? And you go, well, gee, I could do that. I mean, like, you know, I could just put some like spots on the thing over here and be like, whoa, okay, I want $100,000 for that, okay? And it's like, I don't think too many people are going to pay me $100,000 if I throw some paint on a canvas, okay? But, you know, because at least you might argue that there's a, you know, I can't paint, okay? If I could paint wonderful pictures, I guess, and then I threw paint on the canvas, maybe then I'd have the credibility for people to pay me hundreds of thousands of dollars. So first, before you can, you know, do abstract art, you have to be at least understand the basics, okay? So we start off with the Gaussian random vectors, and you have to fully, thoroughly understand those before you can really understand the non-Gaussian case, okay? Now, Bernoulli random variables. So here, this thing is discrete, and it can be equal to 1 with probability theta and 0 with probability 1 minus theta. And you can write down the probability distribution then for a vector of those things. Okay, so like here's a scalar. So let's say x then, it can take on the value 0 or 1. So if it's, you can actually just go through this. And if x is 0, it'll come out to probability theta. And if x is 1, it'll come out to probability 1 minus theta. Okay, so it all works. But you can rewrite it, and this seems sort of counterintuitive, but you need to read the notes carefully, okay? You can rewrite it this way, and sometimes that's going to be useful, and it's hard, we'll worry about later why. But in general, then, you can write down the vector. Now, this is something you need to understand that maybe is going to, like, bog me in mind a little bit, but when I can write P of x, okay, x here can be a vector. So it can really have multiple components, x1 through xn. That may bother you because I didn't make it bold-faced or put an arrow over it or anything else, okay? You're just going to have to get used to it because I'm the teacher and it's too hard to change me because I'm too old. You're going to have to get used to my standards. But my argument for why I don't put bold-face and everything here is that you can go crazy with bold-face and double flashes and all. In the end, it's just a thing, and I'm calling it F, and it all makes it a lot simpler to not get too worried about it, okay? But then in any case, so then you can write down the probability density for this vector x, and this is the form it's going to have, okay, for the, and this is a case where it's identically, independent, identically distributed. We often consider cases of independently and identically distributed random variables because there's an assumption that we're having independent experiments, like in a Monte Carlo test. So you place your bet, here's some outcome. You place your bet again, you flip the coin again. The independent flippings of the flips of the coin are independent because one doesn't have any impact on the outcome of the other. So we'll often consider that in problems, that we have sequence of independent observations. Actually, it's the basis of the law of large numbers and what we're going to later call frequentist estimation. Okay, now, let's see, what over is going on here? Okay, so you can go through this example, blah, blah, oh, this is important, okay? You gotta read this carefully, okay? Now we're gonna have a concept of a statistic, okay, a statistic. So a statistic is when if I observe a sequence of independent Gaussian random vectors, and I want to estimate the mean and the covariance, okay? So I can write down the joint distribution, or this is actually, I can write down the joint distribution, it's the product of the distribution of each vector. This is starting to get abstract, okay? Because each vector has dimension, I think I'm using the letter P, right? But there's n of them. So this matrix here is P by n, okay? It's very important to get that in your head, okay? And now what's going to happen is this is the joint distribution, right? And it turns out that if I write this thing here is a statistic, okay? It's called a statistic because any function of the random variables is called a statistic. So it's the information we're going to collect about the data that we'll use later on, okay? So here what I'm going to do is I'm going to calculate, this is essentially like the sum of all the observations, the vector sum, and this is the sum of all the covariances, okay? So I call it D and F. These things are called statistics, and there's also a thing called the sufficient statistic. You're going to have to read this carefully, okay, because I'm not going to go through it right now. You need to look at this, and it turns out anything with this form is a sufficient statistic. And what a sufficient statistic means is it contains all the information you need to estimate any parameters of that distribution. That's why it's called sufficient, because you got everything you need, okay? Now, sufficient statistics are going to be very important, okay? Now, one thing that's very important is this equation 2.6 here, because equation 2.6 gives us the form and it's not obvious that this is true, but you can go through and verify that this is the form of the distribution for a sequence of independent, multivariate Gaussian random vectors. This is going to come up a lot. So you need to study that and make sure you understand it, okay? And from this, we can do various things. One of the things we're going to do is estimate parameters. So we'll want to estimate parameters like the mean and the covariance. And what do you think a good estimate of the mean is?
Expectation.
Excuse me?
Expectation.
Okay, well the expectation is the mean, okay?
So the average?
It's the sample average. Thank you. Wow, really, you guys are good, okay? I'm really impressed. It usually takes forever to get that answer, okay? If I observe like 10 people and I want to compute the mean height of those 10 people, what I do, I take an average. That's probably a good estimate of the mean, right? The mean is a number, but the average is a statistic. Statistics are random variables, and expectations or means are numbers. So people in the news media say that, okay, so we're running out of time, so I'm just going to leave you with this thought, and it's your responsibility to finish reading this section, okay? But I want to leave you with one thought, okay? That in the media, if you read in the paper, the mean and the average. Average. I can't spell, okay? Everybody knows that the mean and the average are the same thing, right? No. In this class, the mean and the average are not the same thing, right? They are totally not the same thing, okay? They don't even live in the same house, okay? They don't hang out with the same people. They're not both people, okay? Because you know why? A mean is a number. This is a number. And this thing here is not a number. It's a random variable. It's absurd to say that the mean and the average is the same, okay? Okay? So, but the law of large numbers says that as the number of observations gets large, the average will converge to the mean, either in probability or the strong law. So I'm going to do the camera at this point and just say, it's been nice seeing you. Bye.
Recording has stopped.
Thank you.